If you're looking for the Uponor webinar, you've found us. We're going to go ahead and get started. Wanted to welcome everyone, and today we have a special presentation from Uponor. This webinar is about hydronic systems. It's a technology that allows homeowners to experience the luxury of living in comfort anywhere in their home. It also saves energy because water has the capacity to transport energy 3,500 times greater than air. Our presenter today is Steve Swanson, customer trainer at Uponor Academy. He holds more than 44 years of hydronic and steam heating experience and has toured the country speaking and training on the concepts of system operation and design. He helped develop curriculum and training for hydronic heating seminars and also contributed to training for the state of Minnesota boilers license. In addition, he also holds a Lifetime Achievement Award from the Minnesota Multi-Housing Association for training and curriculum development. Now, if you have any questions during the course of today's presentation, you can submit those for our guest by using the small box at the bottom of the Q&A. I'll review those questions and pose them to Steve during the Q&A time set aside after his presentation. Steve, welcome to the program.
Thanks, Mike, and thank you all for spending the time to come to this webinar. I know that this is time you can't get back, and so you've invested it because you believe in something. And so I'm going to try to make it worth your while to come here today and listen to this. And I'm assuming because you're listening to this, you believe in sustainability, and so do I. But most of the time, if I'm going to believe in sustainability, I feel like I have to throw comfort out the window. You might feel the same way. It just makes sense. If I'm going to be sustainable, then comfort isn't really part of the equation. And if I'm worried about comfort, then somehow I've compromised sustainability. And so when I'm cold, first thing I do is turn up the thermostat, which somewhere in the building turns on a boiler, a pump, a burner of some kind, another pump, a fan. And now I'm consuming fuel and electricity. I'm just like I've declared war on sustainability to make myself comfortable. So yeah, I feel a little guilty doing it. But at the same time, if I just throw a sweater on or put a blanket around myself to keep warm, well, I'm not comfortable either. So I'm wondering, isn't there a middle ground? Isn't there a happy medium between that? I think there is, and that's what we're going to talk about today. And so to do that, I have some good news and I have some bad news. The good news is not one single bit of energy that was at the moment of creation has been lost. Not one single bit, not one single BTU, not one single calorie, not a single watt, not a single therm. No amount of energy is missing from the original lot. Albert Einstein said this in his first law of thermodynamics. He said energy can't be created or destroyed. And so that means energy is literally everywhere. This is the good news. There's energy in the wind, there's energy in the sunlight, there's energy in the waves of the ocean, there's energy in natural gas, there's energy everywhere, and there's energy in each and every atom that exists. Now, you probably remember the equation, E equals mc squared. That goes on to say that all the energy that exists today can't be destroyed. It can be changed into something else, but it can't be destroyed. Now that's really good news. Now, here's where it gets just a little weird. Since it can't be created or destroyed, you can't save it. You can't save it because it can't be created or destroyed. So saving energy is paradoxical at best. So what in the world are we talking about? Well, to me, that means you've literally won the energy lottery. You have almost unlimited energy in the universe. So go ahead, spend it if you want. Turn that thermostat up a couple 5 degrees or so. Well, hold on a minute. I've got some bad news. Here's the bad news. Currently, all of the energy in the universe is tied up in the legal department right now. So we don't have access to all of it. It's like having money in your checking account, but you don't have the right to spend it. And in our case, We have all of this energy available to us, but we just don't have the technology to get it out yet. So now we have two kinds of energy that we have in the universe today: available energy and non-available energy. Energy that's not available yet because we don't have the technology to do it. And so we have to rely on what available energy we have left to us. In our available energy further breaks down into renewable energy sources and non-renewable energy sources. Renewable energy sources like the wind, the waves, the solar, those, if I use them, there'll be more tomorrow. I can use them and reuse them and reuse them. But I have non-renewable sources too, like oil, gas, and coal. Once these are gone, they're gone. Now again, I haven't destroyed them. I've used the energy in them, and that energy has converted into something else that at this time is not available to us because we don't have the technology. And some of our available energy is so expensive to get it or to use it that it's really not economically feasible to harvest them at this time. So that's the bad news. We have to work with our available energy in renewable and non-renewable sources. And if I want our children and your grandchildren to have the same lifestyle that we do, then we're going to have to start thinking about how do we save using some of this energy until we learn how to exploit some of these other types of energy. Are you with me so far? Good. Now, we often talk about sustainability and efficiency in the same swimming pool. And although they are like each other, they're not exactly the same. So efficiency isn't always the thing that will help me become sustainable. Just because I make something more efficient doesn't necessarily mean that I've made it more sustainable. For example, if I produce 100 million cars that get 200 miles to the gallon, that makes me more efficient, but at the end of the day, doesn't make it more sustainable. You see where I'm going with that? And on the same token, suppose I make a boiler that's 90% efficient. That means that 90% of the energy goes into the home. The other 10% goes up the chimney to the outside. However, if we look at this close enough, the other 90% eventually ends up on the outside of the house because of heat loss. Again, 100% of the energy still ends up on the outside of the house. And so efficiency, although it's a component and a valuable one, is not the answer. Sustainability is. And that's where sustainability comes in. How much can I spend right now of the available energy that I have to ensure that my children and grandchildren have a like style of living for tomorrow? And so sustainability, more than a science, is really a thought process that defines how much can we consume today at the risk of starving tomorrow. Now, in the process of this, I just want to be brutally honest, I'd really like to stay comfortable in the process, if that's at all possible. I really don't want to go back and live like they did 100 years ago. And people say, well, now that would be the ultimate sustainability. Well, I must say, in all honesty, I'm just not ready to do that right now. So is there something else I can do that makes me part of the sustainability family that doesn't require me to go live in a log cabin somewhere? So sustainability then is going to affect every part of my life: my food, my clothing, shelter, energy consumption, travel. All of these things are part of the sustainability because we have a limited amount of available energy left. Now, sustainability then becomes like an energy 401k program. I'm willing to put a little bit away so I can spend some tomorrow. So you see that sustainability is more than more of a philosophy than it is a science. I'm philosophically analyzing how much I have to stop spending so that someone in tomorrow also has a little bit to spend as well. And so what does this mean to you and I? Well, it means if I build the most energy efficient home that there is using the most technical science that's available, but continue to use non-renewable sources to generate this heating or cooling or lighting or whatever else it is, I'm still ultimately contributing to the global melee that's going on concerning sustainability. I'm losing the game. And so we're looking for ways to choke off that non-renewable energy part, looking more towards the renewable energy part. And well, let's take a look at what that means to us as we compare that to heating. So in the world of heating, I just want to transport the dialogue we've just had into the theater of heating, which is just one of the many cul-de-sacs of energy use. You have lighting, you have transportation, you have all kinds of energy use that you do. And so we're just going to talk about this one small world of the energy and cul-de-sac right now. And so we also know, don't we, that heat rises, right? Heat rises, right? I see a show of hands, yes, no? Actually, heat doesn't rise. Hot air rises. Heat always goes from hot to cold, and it doesn't care what direction it's going. It doesn't matter if it's going sideways, up or down. Hot air is more buoyant than cold air, so it rises. But heat always flows from hot to cold in one of three ways: conduction, convection, and radiation. And you might, if you take a look at this drawing, you'll see I have a fire going there. And if I hold my hands up, the convected part is the fire heating the air, which then heats my hands. So I've got a two-part system there. If I use conduction, I put a poker into the fire, the poker becomes hot, and that heat travels up the piece of iron to my hand. And so I have a transfer of heat by touch. And radiation uses electromagnetic waves to heat me. So there's no energy spent from the time it's created until the time it reaches my hand. Those are the three types of the flow of heat. And it doesn't really matter, particularly radiation and conduction, what direction they are. It could be sideways, up, down, it doesn't matter. Convection, on the other hand, because it's heat rising, generally you need to push air around to make it do what you want it to do. Now, radiant heat works, radiant itself is a form of energy in the form of an electromagnetic waves, which are emitted from a source, and they travel through a transparent space until they hit an opaque surface with a cooler temperature, and then they're absorbed, and as they're absorbed, they give up the energy that goes with it. And so the radiant temperature from the sun travels 93 million miles through minus 400 degree temperature and reaches the earth with no loss of energy at the speed of light. So it travels very, very fast. Now, in those waves, there's no temperature in the electromagnetic waves. There's only energy in there. The energy isn't transferred to temperature until it touches the earth, until it strikes something opaque in the earth. If it's going through anything transparent, it won't give up any of its energy, only when it strikes something opaque. And you've experienced this, I'm sure, if you're sitting at a campfire and you have a cold night on a campfire, and you sit close, the radiant waves go right through the cold air, strike you, and warm you up, and you feel really warm there. Now, if we could take that same scenario and make that electromagnetic waves come from all sides, I bet you'd be pretty comfortable. And it's a very efficient way to transfer energy. Now, let's take this another step. I have another ingredient to talk about. Now, suppose this is my house. Lovely house. Now, suppose I continue to wrap all these little shells in insulation, and I continue to wrap them, more insulation and more insulation and more insulation. What happens to the heat required to heat it? As I'm insulating it more and more, the amount of heat necessary to sustain its heat drops way off. Now, going back to what I said before, if I stop the flow of heat from going into the house, what happens to the heat that's in there? Eventually, it's going to leak back outside. But the amount of insulation I have, or if I stop the infiltration, will lengthen the time that the heat stays in the house. So let me just ask you this. Do you think that there's a theoretical point in which the heat from my own body could overcome the loss of heat going out from my house? That's to say, could I overcome the heat loss through the heat gain of just the heat from my body? And there is actually a theoretical point where that actually could happen. Unfortunately, you'd probably die in the house from lack of oxygen, but at least you'd be warm until then. So we're all in agreement that eventually the energy that I brought in is going to leak out somewhere of the house. And we want to control the rate and manner in which it does that. Now, speaking of that, as I super insulate the house, I do have to be, I'm concerned also for indoor air quality and indoor environment quality as well. And we have these 5 puzzle pieces of the indoor environment quality, IEQ, that are represented by indoor air quality, such as volatile organic compounds that are in matter that we buy today, formaldehydes, paints, adhesives, solvents, propellants. Use ammonia around the house for cleaning. And then I have microbial contaminants such as mold, bacteria, Legionella. I have carbon monoxide, radon possibly, pesticides. I mean, these are all things that can happen in the indoor air quality. If I move over to the indoor comfort quality, ICQ, these are things that relative humidity, temperature drift, stratification, that is where hot air rises and leaves the floor cold, operative temperatures, the metabolic rate of the people in the room has an effect on your indoor comfort quality. And asymmetrical temperatures, like when you walk in front of a really cold window in the middle of winter, you'll notice that it feels really cold. Well, that isn't because of air temperature. That's because your body is radiating heat to that cold window. And so you notice that I could have indoor comfort quality where I'm quite comfortable, but if the air quality is no good, that means my indoor environment isn't a good place to be. For example, I can be quite comfortable in the basement in the middle of summertime, stay nice and cool down there. But if there's radon leaking in or leaching in through the walls, then it's dangerous to be there. So indoor comfort quality has to be balanced with indoor air quality as well. I also have indoor sound quality, fan noises, air velocity, vibration from equipments, humming noises, all of that stuff affects the quality of my indoor environment quality. Lighting does as well, indoor light quality. If I have solar gain coming from light from the sun passing through the windows and reflecting back out into the house, creating warm spots in the house and cold spots in other because it shuts off the heat, then that's contributing to it as well. And finally, I have indoor odor quality. Paints, cooking odors, musty. You know what it's like when you cook something smelly down in the kitchen, and that permeates through the whole house after that. So these are the 5 areas that make up indoor environment quality. And you can see the temperature, the indoor comfort quality, only makes up 20% of the comfort pie. We put so much stock into making sure that the thermostat's satisfied that we forget to satisfy the people that live there. So the thermostat is nothing more the ambassador for my comfort. Only one part of it too, just my temperature. Now, I was speaking about the indoor air quality before, and I want to show you this picture. This is a basketball. Now, the thing about a basketball is it's just about 1 cubic foot of air in there. Now, I have to have so many air changes per hour in the house to make sure no one gets sick or has enough oxygen, all of those. And here's one of the things where the sustainability really comes in. So suppose I have a 2,000 square foot house with an 8-foot ceiling. That would mean I have 16,000 cubic feet or 16,000 basketballs. Now, if you imagine for a minute that I have 1 air change per hour, that means I'm going to be taking 16,000 of these basketballs and putting them outside and then bringing in 16,000 fresh new basketballs. But these are going to come in without the energy in them that I just put in there. So all day long, I'm going to have to continue to send basketballs out, bring basketballs in, and every time I bring them in, I have to reheat them again. Now you can see if I could change the air changes per hour, even to a half of an air change per hour, I'd go from 16,000 basketballs to 8,000 basketballs. I'd feel exactly the same. My house would be exactly the same. No one would ever know in a million years. However, I've just saved having to heat 8,000 basketballs. Now to carry that one step further, if I go to a third of an air change per hour, now I'm down to just over 5,000 basketballs. So I started with 16, I'm down to 5. And nothing's changed in the indoor environment quality of my home, except I haven't had to pay for 11,000 basketballs. So you can see we have a problem with this indoor air quality and heating and temperature. And, you know, you can fix it, but there's always a price tag attached. And so what we're trying to do is to balance those out to find out how can we, what's the best solution for a good heating system for my house. Now, I don't know if you knew this, but you're a little BTU manufacturer. If you look at these red thermographs, you'll see the darker the color, the more heat they're giving off, the red areas. And that red shows up in the form of electromagnetic energy. That is the same thing that's coming from the sun, electromagnetic waves. Now, every human produces about 500 BTUs per hour when you're sitting there idle, somewhere around that. 100 of those BTUs you need to metabolize your food and turn it into energy for your body. The other 400 are constantly being shed from your body. The rate and manner at which you're shedding those determine if you're going to be comfortable. Now, those 400 BTUs are lost, 50% of them are lost through radiation, 30% through convection, and 20% through evaporation. And so you can see that if I go back just for a moment over here, you are a net BTU manufacturer yourself. Now, the rate, your body is not capable of telling temperature. It can only tell differences in temperature. Your body can't say, well, I feel hot or I feel cold. It's actually measuring. You have about 200,000 sensors on your body that are constantly measuring, is heat leaving or not? That's all it can tell. If heat's leaving quickly, then I'm going to feel cold. If heat's not leaving too quickly at all, I'm going to feel hot. And that's how your body tells you whether you're hot or cold. It's not really the temperature, it's how fast the body is losing its heat. I can give you an example of this. If you take your hand, right now, take your hand and put it on the table that's next to you. Go ahead and do that. I see some of you aren't doing that. Take a minute to do that. There we are. Okay, do you feel that the table's cooler or warmer than the air around you? Now you'll probably say it feels cooler, but you know it's been sitting in that room for a long time. It's exactly the same temperature. It just feels cooler because you're now touching the table. It's conducting heat out, which is so much better of a heat transfer method than air. So that's why when you sit next to a cold sofa or something, you feel colder, even though it's the same temperature as the air, because by conductance, you're losing all that heat. And we lose it, a lot of it, through the radiation, and then convection and evaporation the same way. So at the end of the day, I really don't need BTUs, I need comfort. And so we're going to start, because I'm making my own, we're going to start designing towards comfort, realizing I'm a net exporter of BTUs. I just need some help controlling the rate and manner at which my body's losing heat. And that'll set me on the path to comfort. Maybe I can have both worlds at the same time, sustainability and comfort. So to do that, we'll take a look at, you may have seen this before. This is the ideal heating curve. This is done by the Department of Energy way back in the 1950s. And it was a measurement of what would be the ideal heating curve for the most amount of people. What temperature would they like to see? And they came up with this after thousands and thousands of people that they tested. They found out that if your floor surface temperature is about 75 degrees, and your heart, where your heart is, up that way by your head, at about 65 degrees, that's where you'd feel the most comfortable. The most amount of people will feel comfortable at that rate. Now, I know there's differences in people's comfort levels, but if I had to model something after what would make the most amount of people comfortable, this is the ideal heating curve. And we've used this engineering-wise for years and years and years to help us figure out how to make a good heating system. And today, there are typically two distinct types of heating systems around there. On the left, you'll see this is a forced air system on the left and a radiant system on the right. Now, if you look closely, you'll see there's a yellow line there, the black line. Let's take the forced air heating curve first. The black line next to where his feet are represents the ideal heating curve, and you'll see it goes up and out just like it should. And the yellow line next to it represents what's actually happening, the actual heating curve used in a forced air system. And in this case, you'll see down by my feet, I'd like to have 75 degrees, but you'll see it's about 62 or 63 degrees down there. Up near my heart, it's about 75, and then because hot air rises, that hot air goes up to the roof, up by the chimney, up in that area up there. And of course, that's sitting next to 10-degree air up there, so I have a great deal of difference between my indoor temperature and my outdoor, so I'm going to lose a lot of heat out that way as well. And the problem is, my feet are still cold. So, and where's your couch sitting in that, by the way? So, to get that heat back, since all my heat's up there at the top, I'll go ahead and put a ceiling fan up there to shoot the heat back down to my feet. So now I've had to install another piece of equipment to get my own heat back, to heat my feet up, and I've become less sustainable in that aspect. If you compare that to the heating curve on the right, a radiant heating curve, it follows almost identically the ideal heating curve. That is, the floor is warm, and it's radiating its heat out, about 60% radiant, about 40% by convection. So I do have some heat rising by convection, but it drops off rather quickly. And again, my feet down where I want to keep them warm is nice and toasty down there. So comfort-wise, I'm quite comfortable, and you'll notice I have quite a bit of turn down on my thermostat to get to the same temperature. I'm only setting it at 65 to get that same temperature setting. And look at the temperature up at the roof next to my 10 degrees. You notice now I have like 55 degrees up there, which is about 40 degrees warmer or cooler than the forced air one. So not as much temperature next to the cold outside air, hence not as much heat loss. Now if I compare these two again, the one on the left being a forced air system, the one on the right a radiant system, again hot air rises, so it comes out of the register, it goes up to the top, the cold air sinks, and is drawn back in to be reheated through a register. And you'll notice it creates a couple of things. All my heat's up at the top where no one lives, so that's not very good. And where I sit down there, if I'm sitting in that chair is quite a bit cooler than I'd like it to be in my comfort setting. So that's why one way you can always tell a forced air house is it always has a blanket on the couch. Every single forced air house I've ever seen always has a blanket on the couch because hot air rises. All my heat's up at the ceiling where I don't need it. Now the radiant on the right is I'm making the entire floor a nice radiant heat emitter. So as you can see, it's much more even going up. The radiant drops off as it goes up, so I don't have quite as bit of that. And I think one of the side benefits of this is I can put that chair anywhere I want in that room. You notice on the one on the left, I can't put it near the registers. So if nothing else, you get a little benefit of where you can put the furniture. Now, that brings, if you notice here, so take a look at this room, relative to the thermostat, where's all my heat? Isn't it above there? So relative to the thermostat, all my heat is up in the ceiling. In a radiant system, relative to the thermostat, all of the heat is below, or most of the heat, I should say. And so that's where I live, that's where I dwell. So I'm keeping the same amount of heat in the area that I'm living at. Hence, I'm getting the same amount of heat being spent, but I'm more comfortable while I'm doing it. So that brings us to the benefits of radiant heat. Number one is strictly the comfort. I don't have to have a blanket on the couch because what I'm going to do is heat the couch up and let the couch heat you up. So that seems quite a bit better strategy to me. Secondly is the energy savings. As Mike was saying during the introduction, water is 3,500 times better at carrying heat than air is. Air doesn't like to carry heat, as a matter of fact. And so this 3/4 inch pipe that you see up in the top carries exactly the same amount of energy as an 8x14 hot air duct. Same amount of energy. Now, what that means practically for you is that I can transport the heat from my heat source to where the heat is needed for considerably less amount of money, because air does not like to be pushed around, as you well know. And air is a terrible conductor of heat. When you're making insulation, isn't the main component of insulation trapped air? So what we're doing, if we're using forced air as a heating system, is we're using insulating material as our heat medium. And I can't imagine that making good sense, but we'll carry on anyway. This is where sustainability really comes to work. In this graph, you'll see that the specific heat of water is 1 and air is 0.24. The density per cubic foot of water is 62.4. Air is 0.074. If you multiply the specific heat times the density, you end up with a figure called the energy transport capacity, the ability of the material to transport heat. And you'll notice that water can carry 62.4 BTUs per cubic foot per degree as compared to air at 0.018. Now, if you divide 62 by 0.018, you'll end up with 3,467, or about 3,500 times more energy. So it's not only a better energy transport, and I'm transporting it out, it does it much more easily. A pump is much less money to run than a comparable fan for the same amount of energy. Now, when I get the heat out to the room, I have to diffuse the heat to make sure that everybody in the room gets the right amount, so that I can be anywhere in the room and still feel warm. And this is where part of the another part of the problem comes out. For example, if I'm using old-time radiators, I'm putting all that heat right in one spot. And so I have to have quite a bit of temperature in a very small amount of space. I'm going to have a lot of convected heat going up to the ceiling. The same with the forced air. If I'm shooting a lot of heat in from a little register into a smaller spot, it's going to be harder to diffuse it through the rest of the room area. Now, if I had a radiant floor down there, what I'm going to do now is, instead of 160 degree water temperature or 110 degree air temperature, I can have an 80 degree floor, and you'll get exactly the same amount of heat, but it'll be distributed over the entire floor, so there won't be this accumulation of heat in one area where you feel it's hot in one part of the room and cold in another. So that's one of the side benefits of heat diffusion. Now, we still have to determine how much heat does my house need. And this is determined by, I have to find out BTUs per hour per square foot. This is the amount of BTUs released during 1 hour for every square foot of my house. And that'll determine how much heat I have to put back into it. And we determine that by doing a heat loss. And to do that, you need things like design temperature difference. How cold is it in your part of the world? I need to know my window R value, exposed walls and ceilings. And anywhere where there's a temperature difference, I have to insulate that to keep my heat from migrating out. And so the farther north you live, if you have less, if you only have single pane windows, if I don't have very much R value in the walls, I'm going to need more BTUs per hour per square foot. And so this is where the insulation versus heat loss battle comes in. Now, back in the day when energy was really cheap and houses were being constructed, I remember doing heat losses from houses that I didn't do them personally, I wasn't there, but I went back and looked. Houses built in the 1930s often had 7,500 75 BTUs per hour per square foot, 75. And they'd use a radiator to heat the house to make that up. And you could, I remember curtains standing out from the wind blowing through the cracks in the windows. It was terrible. And so a poorly insulated home now is anything that's above 30 BTUs per hour per square foot. We consider that a poor insulated home. I'm going to have to put quite a bit more energy in there just to keep up with it. And you can imagine with that kind of heat loss, I'm not going to have a quality heated home. Now, in about the 50s, they started getting better with it, and they made R11 in the walls and R40 or 35 in the ceilings. And you'd get anywhere from 20 to 30 BTUs per hour per square foot from a house built back then. Again, not as efficient as you'd like it to be. Now, the energy codes of today generally require an R19 walls, R43 or 48 ceiling, depending on where you live, R2.5 glass. And so we're down in the 15 to 20 BTUs per hour per square foot range for a good home. And radiant heating works very, very well in all three of those other ones to provide good heating at a comfortable range. Now, super or high performance homes, on the other hand, are anything that's 10 BTUs per hour per square foot or better. I just saw a house done here in Minnesota that had a heat loss of 8 BTUs per hour per square foot. So again, if you had a 2,000 square foot house at 8 BTUs per hour per square foot, I could heat the whole house with 16,000 BTUs in the dead of winter. Now that's just about the same as my Coleman camp stove, I think, puts that much out. Now let's take that up a step. Suppose I have a 2,000 square foot house with 15 BTUs per hour per square foot. I'm going to need 30,000 BTUs to do the same job. See the difference? Same, I'll feel the same inside the house. Nothing will be different, but I will have saved burning up that much natural resources to get the same amount of heat. That's why insulation is becoming such an important factor in today's home. Now, I know the debate rages whether radiant heat is a good choice for high performance homes. And I would love to make that argument perhaps at a later date. But just go on to say, I think there's some reasons that type of radiant heating will work just as well if I switch to a low mass radiant heating system. I'm able to do some things where I end up with a warm floor and a low output at the same time. So how can I replace the heat that's being lost? I can use a furnace, which again, I'm heating the air and the air goes out, and because it's hot air, it will rise to the top. I have to recirculate it. I think that's an option. It's an interesting point to note that in North America, 95% of the homes built in North America are built with furnaces today. In the rest of the world, it's exactly backwards. 95% of the rest of the world outside of North America uses hydronic or radiant heating to heat theirs. So, because their gas prices are $12 a gallon, I think that's probably why. So that's the difference. I can also use hydronic heating in the form of radiators or baseboard heat. They require higher temperatures, and again, I put my heat sources in one spot again, so getting comfortable in all areas of the room or the house becomes a bit of a problem in there. Or I can use electric heat and a baseboard type heat, and I know I've heard it said so many times before that electric is the only one that's 100% efficient. That is just not true. I know you get 100% of the output from the element that's there, but manufacturing electric heat is a very expensive proposition. If I'm burning coal to produce electricity, and then I have to transport it over long wires, that energy transport cost can drive the cost down to as little as 25 to 30% efficiency over the total system. So I know that thing it's often made, but I don't think it's the right one. Now, lastly, I can replace it with radiant heat as well. Now, the benefit of radiant heat is I can lower the water supply temperature in the floor because I'm making the entire floor a heat emitter. I'm not putting it all in one area like I would with a radiator. I've moved it all over. The entire floor becomes a heat emitter. And so you find a much more even flow of heat through the house. And I find I don't have, because it's not stratifying, I don't have cold spots, warm spots, and I don't feel drafts. I don't hear noises from that. And so if I want to move the heat to this lady, I can do it with air or I can do it with water. But let me just show you a little chart on the bottom, on this next page. This is a surface temperatures that I would need for a heating system. Suppose I needed 15 BTUs per hour per square foot. So we see that right there. And suppose I want to set the thermostat at 68 degrees. That would mean I would have to have the floor temperature at 75.5 degrees to make 15 BTUs per hour per square foot. Nice warm floor. Remember the target temperature we were looking at when we first started for the comfort curve? Didn't we say it was right around 73 to 75 degrees? Well, here you have a nice warm toasty floor producing the necessary BTUs, and I'm only having to have a 75.5 degree surface temperature. So how can I put these systems together? I can use a radiant floor. I can install the tubing in a slab. These work tremendously well for typical homes built to code today with R11 or R19 walls, R2.5 glass, because it's a high mass system. So it gives off its heat evenly over a long period of time with a very low water temperature, often in the 80s. 80-degree supply water temperature will produce that nice warm floor that you're looking for. 1,000 square feet of concrete holds 49,000 pounds of mass. That's a lot of mass. That's a lot of mass. So once I heat it up, it stays heated for a long time. Another way that's used quite often is gypsum, gypcrete overpour. It's a light, soupy mixture of elements that adds about 15 pounds per square foot to your 15 to 18 pounds per square foot to your truss system, so it's not overbearing, and it adds a nice layer of sound deadening between you and the floor below. It's very comfortable. And just embed the tubing in there, and I'm done. Another way, this is another type of product, knob. It's a fast track, we call it, or a knobby mat. I just put the knobby mat down, run my tubing in it, and then pour gypcrete over top of it. So this is a way I can retrofit and have the comfortable radiant heat, and at the same time, not raising my floor temperature too terribly high. Many people prefer the grooved plywood, what we call quick track. It's just plywood with grooves in it. You put your tubing in it. This is an excellent choice because it is a low mass system. This is an excellent choice to be used in high performance homes because I'm not holding a lot of heat in there. It's much easier to control. And I'd go back to say I would address the high efficiency homes. One of the reasons high efficiency homes don't work particularly well with radiant systems isn't the radiant system, it's the control system that operates the radiant system. If you're going to use a high performance building with a high mass system, if you put a slab sensor in there to control the water through the slab, you can have good heating without overheating the house. But that's a control issue, not part of the problem. I can put it underneath the joists if I want for joist heating with clips or staple up, or I could put aluminum transfer plates up in there to help reduce the supply water temperature, which will give you the same surface temperature on the other side. But again, I'm back in the 80s, high 80s to run water through there. That doesn't take very much from your boiler. And if you're running in the high 80s, that makes your condensing boilers very, very efficient. Don't forget, you can do radiant ceilings because the heat still, the radiant part of the heat goes right through the air and until it strikes an object. And so I can have, if I want to retrofit for in a garage that's already got a cement floor down and I want to put radiant in the garage, I can put some radiant ceiling up. I can put it in a house, a brand new house. And boy, I'll tell you, that feels mighty toasty. When you've got radiant ceiling in there. If a radiant floor isn't available, this is a good option, as is a radiant wall. I can put it in the wall and radiate out from there. In this picture, you'll see it sitting right next to a big walk-in door there. The benefit of this is, you know that cold feeling that you get when you walk next to a plate glass window in the dead of winter? This takes that away. So you feel absolutely toasty right next to a plate glass window. That's kind of cool, I think. I can use any type of flooring covering I want over radiant systems, the same as before. I can use tile, wood, carpet, all of those. The difference is, if I'm tile and wood are very good alternatives for that, but carpeting slows the transfer rate between the floor and my air surface temperature. So if you're going to use carpeting, I would suggest you use one made for radiant heating. You'll get a much better feeling out of it. But nothing feels quite the same as a nice hardwood floor with radiant heating in it. And I can get creative. On the picture on the right, you've all been in the bathtub in the middle of winter or in the shower and touched your shoulder against that ice cold wall. That doesn't feel good at all. If I put some radiant tubing in the wall there, now it's like taking a shower in a cocoon. You feel absolutely special in there. I'll tell you, it's quite the feeling. And I can get creative. I could put a little radiant tubing underneath that granite slab that's in the kitchen. You know how cold that thing feels in the dead of winter. Well, now it becomes a heat emitter, and quite a good one, I might add. And so if you just want to heat a small area, this is a good alternative for you to do. So I've talked about the ways of using radiant heating. We've talked about the benefit of using those, and I just want to wrap it up by saying thank you for coming to this, and I'll stand by for some questions, but I hope you've seen that there is a comfortable way that I can be sustainable.
Thanks, Steve. I really appreciate that, and we'll remind our audience to utilize that Q&A box. Go ahead and send in your questions now, and we can get them on to Steve. We're going to go ahead and start with a question from Louise. He wanted to know, is there an expansion and contraction on wood floors due to the change in temperature?
Oh, that's a great question. Again, Luis, the benefit of using radiant low temperature heating in there is, you have to remember, I'm only heating it up to about 80 degree water, 85 degree water, 87, somewhere in there. So we're not talking hot water. It's just warm, tepid water that's going through there. So the expansion and contraction is if I run too hot of water through there, you're right, I would hurt the floor. It could cause cupping. But that's why that's why you put controls on it, to keep it from not going over those limits. And with radiant floor, you're nowhere near the supply water danger with hardwood floors.
Steve, I had a question. You talked before, you use the imagery of the basketball to demonstrate the air changes.
Mm-hmm.
And some in our audience might have heard of the ACH 50 requirements in the energy codes, but they might not be fully familiar with what that means. Is there a way for you to explain air changes relative to ACH 50 with using the basketball analogy?
Well, the existing codes today require a certain amount of air changes per hour in order to keep enough fresh air for you to breathe, and to make sure the volatile organic compounds are being taken out, fresh air being brought in. And so in light of the energy code themselves, what they're saying is, if you're going to be exchanging air in and out of the home, they want you to put some way to capture that energy, like an HRV or some way of capturing that energy, so you're not just shooting 8,000 basketballs full of hot air and bringing in 8,000 cold air. So many of the new energy codes require that you have a heat recovery ventilator on your home, that as the warm air is going out, it's passing by the cold air coming in, and it transfers that heat from the warm air to the cold air, and it warms it back up coming in. At the end of the day, you still lose about 15% though, even in the HRV.
Okay.
So I
Question from
still have to
Nancy.
put some more basketballs.
That's okay. Question from Nancy. She wanted to know, what type of tube would you use for the water system?
Well, I'd certainly prefer that you'd use Uponor's tubing. It's a PEX A type of tubing made specifically for radiant heating. It'll handle the temperatures extremely well, and it's the amount of diffusivity that the tubing has. Isn't that a nice big word? The amount of heat that it will distribute is very, very good. And so it's not prone to puncture like copper or erode like copper. It's extremely less expensive than copper. So I would use, if I were putting a floor in today, I would use a PEX A tubing of some kind.
Michelle wanted to know if there were any issues with the radiant tubing bursting and what precautions that could be taken to eliminate such hazards.
Well done. Well, anytime I heat water, water expands. The good news is the hydronic people have known this for centuries. So on your system already is an expansion tank, which is designed to take up the extra expansion and keep it at one constant pressure, usually about 15 psi in your home. That's all you need in pressure-wise. So you're not talking a good deal of pressure. Then the boiler itself comes with a 30-pound relief valve. So If the expansion tank doesn't get it, the relief valve will. And our pipe, we burst our pipe here at the factory at 800 psi, so you can see we're nowhere near that. Well, we don't like to call them boiler explosions because that implies you've done something wrong. We like to call them unscheduled equipment relocations. Doesn't that sound nice? So if my boiler relocates to Des Moines for some reason and leaves the boiler room, it won't be because of the tubing. It'll be because the relief valve failed. The tubing won't go. The relief valve won't.
That was very PC, Steve. That was nice.
Thank you.
Douglas had a question because you've been speaking a lot about residential applications. How does this apply to commercial buildings? Because I would think there would certainly be some overlap there, but are there any specific things that apply to commercial buildings that maybe wasn't touched on?
Um, the only difference is in a commercial building, like let's take a Walmart as an example. They're not quite as concerned about floor comfort as a home would be, since no one takes their shoes off when they go into Walmart. So they're concerned more about economy. That's why they're putting in radiant heating systems to begin with, because it's economically less money to install and operate than forced air systems, and I can run it at a wider delta T that means the water temperature coming in and out. I can widen that a little in commercial because people keep their shoes on. So it's actually, it works even better in commercial than it does in residential.
We get a question from Matthew. He wanted to know, how often do you need to flush these systems, and does that depend on the hardness of one's water?
Awesome question. I have a hydronic system that I've been taking care of for almost 30 years, and I've never changed the water in it one time. It's a closed loop system, so unless someone punches a hole in it or a pump breaks and lets the water out, the same water you put in 20 years ago should still be there. It's not going anywhere. And so therefore, the hardness of the water isn't particularly even an issue. That first little bit of water that's in there will settle out in wherever in the boiler it wants to settle out, and then it'll run 25 or 30 years without any treatment, it won't need anything. You're going to remove the oxygen with a spiral vent or some form of oxygen diffusion that you're going to use. And once that oxygen's out of there, rusting can't happen. Most of the compound breakdowns can't happen because there's no oxygen there to do it. And so therefore, the water most of the hardness stays suspended in the water and runs just fine for 20 years.
And there's no evaporation.
None. No, it's not evaporating anywhere. Better not be. It's not
right.
supposed to. If you have some evaporating water or water loss going on, you may want to look into that. It shouldn't be doing that. You should be able to put it in, and 20 years later, it should still be there.
Question from Elizabeth. Can these systems utilize a solar hot water system?
Oh my, yes. That's the benefit of this, is particularly if you can get a little solar with a little stored water. Now you're talking sustainability, because now I'm using renewable energy to heat the floor, and solar and the two applications that work really good with radiant floors are solar heating and geothermal heating, and both of those are renewable. So they both have their place with radiant. The very best, according to the Department of Energy, the very best, most efficient system to use today is a geothermal system with a radiant floor, according to the Department of Energy.
Got a couple more questions in the queue, Steve. You mind sticking around a little bit past the top of the hour?
Sure.
Okay. And also, I'll make the last call to our audience. Got any last-minute questions, please send them in. We certainly appreciate all those that have come in so far. David had a question. You talked about heating, but can these systems be used for cooling as well?
Yes, radiant cooling. I don't know how familiar you are with the LEED program, the Sustainability LEED program. It'd be worth another look at that someday. But they're the ones who evaluate how sustainable buildings are. And LEED programs today, you can't, you can't qualify for gold or platinum without using radiant cooling. And that's how enormously sustainable radiant cooling is. It works extremely well. Now, you talk to anybody who's sizing a forced air system, first they have to size it for cooling, which is about 70-30, 70% more, 30% for heating. So it's forced air cooling takes a ton of energy. So putting it in the slab works very good, and you just keep the temperature 2 degrees above the dew point, and it'll never condense. You don't have to worry about it condensing, and it's a very effective and efficient way of removing heat from a building. I can't remember the last time I've seen a commercial building go in that doesn't have some component of radiant cooling in it somewhere.
So even though the hot air rises, you in the cool air, the radiant cooling would be in the tubes and the floor, you're still going to be cool.
Oh my, yes. Again, we're not creating cooling, we're removing heat.
Okay.
So this is where radiant cooling in the ceiling really works good, because if I put the panels up in the ceiling with, it's not cold water, it's just slightly chilled water, when that hot air rises, it'll hit that, fall right back to the floor because it's cooler. And so it sets up its own convective circuit to recirculate itself around the room. You don't need any fans to do it, and you feel nice and cool. So radiant ceiling works terrific with radiant cooling.
Final question that I'm seeing here comes from Madeline. Does this kind of system work well in a combined heat and power scenario? And I know CHP is kind of a big concept, but if you touch on it just a little bit.
Again, energy in, energy out. As long as I found, if I were doing that type of system, I would make sure it's balanced with a real good insulation program, and then they work extremely well. So that's one of those systems where you have to be on board with your insulator to make sure that works correct. So you don't get drafts, you don't get cold spots. I can't let my outside walls in that scenario get cool, or you'll have some comfort issues in the home. You'll still get heat, of course, but you just won't have as much comfort. That's why, again, radiant, when radiant is coming out, it doesn't just hit you, it hits the walls and the furniture, and the walls become warm, and they sort of become another heat source for the rest of the room, a little bit more convective heat off from the warm walls. And so that's where she would like to hitch that system up to.
Gotcha. Well, I don't see any other questions, so I want to thank Steve for sharing his time and knowledge with us today. Very much appreciate it. I appreciate, too, our audience and the wonderful questions they sent in as well.
Well, thanks for having me, Mike. And thanks to all of you for listening.
Now, the Impact series is going to return in 2015. We're working to book guests now, so stay tuned for news on the next webinar in that very thought-provoking series. Until then, everyone have a great holiday season, and we'll see you back here next year. So long, everybody.